Okay, we're going to start talking about section 10.1 on parametric equations. Chapter 10 is about parametric and polar curves. So all the way through calculus so far, we've looked at things in the form y equals some function of x. There are reasons that we want to look at curves defined in a different way. Some of these are that we can't always get just one function to define a curve in the plane or in 3 dimensions. Sometimes we can't get a function at all to describe a curve. And parametric equations let us do that. They also make things a little more simpler for some kind of weird curves. And they're going to mean a lot in Calculus 3 when you start looking at modeling trajectories of moving objects. Okay, so basically what we have going on right now is we have our standard 2-variable description where we have a function f and y is given as f of x. What we're going to do now is introduce a third variable that's a parameter t. We're going to define a curve by 2 different equations. X is f of t and y is g of t. There's a couple different ways to write that. You might see it written separately as x is f of t, y is g of t, or as an ordered pair, f of t, g of t, and you have to set some range on the parameter t. That's a really important part that gets forgotten quite often. Okay? So, one other thing that we need to look at here is discussing forward or positive orientation. So the direction in which a parametric curve is generated as the parameter increases is called the positive orientation of the curve. A lot of times we think about t as time, but it doesn't have to be. Whatever the parameter is, as the parameter gets bigger, the direction that you're drawing the curve is the positive orientation of the curve. A couple other important things that we need to consider are parametric equations of lines and parametric equations of circles. Let's start with lines. For a line, the equation is going to look like x is x0 plus at and y is y0 plus bt, where x0, y0 is a point on the line and b over a is the slope. Note, things can get a little weird, of course, with vertical and horizontal lines, but this works for most lines. Okay, the next thing that we want to look at is circles. And parametrically, circles are going to have equations that involve trigonometric functions. So here we have x is 4 cosine 2 pi t, y is 4 sine 2 pi t for t between 0 and 1. In fact, this could just be done with a cosine bt and y is a sine bt. This can be done very generically. And when you square both of these and add them together, notice what happens is you just get the a comes out and you get x squared plus y squared is a squared. So like on this one up here, this would just work out to x squared plus y squared is 16. So that's the circle that you're sketching. Now the part of the circle that you're sketching depends on this parameter over here. You might not get the entire circle. You might just get half of the circle or a quarter of the circle or some little part of the circle. That depends on the t. I wanted to show you a little bit more about what I was talking about with the circle. So here's a very simple one, sine of t and cosine of t. So again, this is x is sine t, y is cosine t. And here I just have t going from 0 to 1. So if you think about this, if you put in 0 for t, you're getting sine of 0, cosine of 0. Well, the sine of 0 is your x value, and the sine of 0 here is 0. The cosine of 0 is 1, so we get the point 0, 1. Then if you go out to 1, you're getting the sine of 1 and the cosine of 1. Well, those are some weird decimal values, right? So you end up over there. I can increase the t. 2, 3, 4, 5, 6. I need to go to 2 pi to work my way around the entire circle. Right now, what happens if I go to 4 pi? I just repeat the circle twice. Right, I'm going around and around. Or I could change this and go 2 pi to 4 pi. I could draw the same circle. Right, I've just kind of changed my parameters. There's all kinds of ways that we could do this. So these values of these parameters really, really matter. Right, you're going to get a different little piece of that circle every time you change these t values. And maybe sometimes you just want that little piece of the circle. Okay. Heading back, there is a more generic form of that equation for the circle. That is here. X is x0 plus a cosine bt, y is y0 plus a sine bt. And those things are going to let you put a center on your circle. So x0 and y0 will be the center. And you still have the a as the radius. So that's very similar to what we had before. We're just adding the x0 and the y0 to get a center for our circle. Okay, the next thing that we're going to do is take a look at problem number 13. So here we're working with parametric equations. They ask us to make a value of t, x, and y, then plot the points in the full parametric curve. So that is like letting t go minus infinity to infinity. Then they want us to eliminate the parameter to get an equation in x and y. That's the thing you can't always do, although you probably can do on most of the problems in the book here. And then describe the curve. So making a table for number 13, I just took some t values. I went from, well actually, they wanted us to go -5 to 5 on this one. So that's our full parametric curve, sorry. So to make a table, I went from -5 to 5 with t values, and then I just substituted in -5 plus 6 is 11, and so on. That goes from 11 to 1 for x values. My y values go from -18 to 12. I plotted those values. They go from 112 to 11, -18. It makes this line. And then for the positive orientation, you think about what happens as you increase t. Well, as t goes up, I go from the 11 back to the 1. So I'm going this way. So that's my positive orientation for this curve. Now, a kind of neat thing, you can do this very easily in Desmos. I put -t plus 6 in and 3t minus 3, x comma y. And I had my t go -5 to 5. And I can see what the final product looks like. Now, if I wanted to see my orientation, I could do this. So I'm looking for my orientation now. I could just like slowly increase the t and see which way the curve is going. Right, so I'm at -5, I go to -4, -2, 4. Right, I can see this curve is just increasing as I increase the t. It's going up this way as I'm laying the blue on top of the red. So that's my positive orientation is headed up. So Desmos is a pretty good tool to play around with parametric equations. You can also do these in your calculator, and we'll look at that a little bit in class. Okay, let's go back. The rest of what we were supposed to do on that problem is eliminate the parameter and then describe the curve. So if we're going to eliminate the parameter on this, we would have to solve these for t. So one thing that we could do here is maybe solve this first one for t. If we did that, we would get t is 6 minus x. And then you could go into here and plug in 6 minus x for the t is, and you would get 18 minus 3x. So in the end, you would end up with 15 minus 3x. So y is 15 minus 3x? That is an equation of a line. And if you double check, that's exactly the line that we graphed already. So that's the way that you can eliminate the parameter, is just using the old substitution method. Okay, the next one that we're going to look at is number 16. For that one, they gave us x is t plus 1 squared, y is t plus 2. They ask us to eliminate the parameter, describe the curve, find the positive orientation. So to eliminate the parameter, I did a little substitution again. T is y minus 2. If you plug that in here, you get x is y minus 1 quantity squared. Well, I know from college algebra that is a parabola that opens to the right and is shifted up 1 unit. So there is that. Then to find the positive orientation, I just plugged in a few t values. If t is 0, t is 1, t is 2, I found the points that corresponds to on the graph. And you can tell that it's going from 1, 2 to 4, 3 to 9, 5. So this curve is going that way for its positive orientation. I have this thing over in Desmos also. There's a little piece of the graph. They actually wanted this to go from negative 10 to 10. So there's the entire thing out to negative 10 to 10. You can see that. Let me turn this other one off. Now, an interesting thing, I have found another parameterization for this. Basically, what I did here was I just made y equal to t and made x equal to the equation of that parabola that we had. Notice that the t values don't match up here. If I have t go minus 10 to 10, I do not draw the same curve. I could figure out what those t values need to be to make this work, but I don't have those right now. Okay, so the t values are definitely different. There are infinitely many parameterizations of every curve. If you don't believe me, I could just make this a 2t and then similarly change this product over here, and I would get the same thing. So there we go. See, all I did was plug in 2t where the t was, and now I have another parameterization of the same curve. So I could just keep repeating that over and over and over again and get infinitely many parameterizations, but the t value needs to change each time to draw the right little section of the curve that you want. Okay. The next thing that we're going to do is look at problem 21. Problem 21, they give us x is 3 cosine t, y is 3 sine t. And actually, let's look at the problem. They want us to eliminate the parameter, find a description of the circles or arcs in x and y, give the center and radius, and indicate the positive orientation. So this is 3 cosine t, 3 sine t for t between pi and 2 pi. So, to eliminate the parameter, I just square both sides. You get x squared plus y squared is 9. So I added these together. We'll square these and then add them together. So x squared plus y squared is 9 cosine t plus 9 sine t. So x squared plus y squared is 9. So that's a circle, center 0, radius 3. So there is that picture, but we're only going from pi to 2 pi. And if you plug those in and evaluate what those are, you're going from negative 3, 0 to 3, 0. Or we know pi and 2 pi is just going to give us the bottom half of the circle. But for the positive orientation, as t increases, I'm going from left to right. Okay, the last thing I wanted to look at was this example. We have x is t squared plus t, y is 2t minus 1. And then we have this other parameterization. I showed you this before, that these are the same right opening parabola. 1/4 t squared plus t plus 3/4, comma t. These are the same right opening parabola. Let's say that I wanted to parameterize this and get the section of this parabola that goes from 0, negative 1 to 2, 1. Well, the way I got this was I decided I wanted t to go from 0 to 1 on the first one. So you get 0, negative 1, and then when you plug in 1, you get 2 and 1. Well, what the heck am I going to do on number 2? Well, what I would do is just set each part of this equal to what I wanted. So if I want to go to 0, negative 1, I would set this first part equal to 0 and see what I needed. Set that part equal to negative 1. And then the same here, set that equal to 2 and solve, set that equal to 1 and solve. It turns out your t has to go negative 1 to 1. And that's pretty easy to tell because the t's are exactly matching up with those. So it's pretty clear you're going to have to go negative 1 to 1 because that's what you need the y values to do. That's it, and I'm out of time. Look at that, 14 minutes and 58 seconds.